one way you can think about indeterminate forms is it's two forces that are competing against each other. For example, 0 over 0 is two forces pulling in different directions. On the one hand, 0 divided by anything equals 0. On the other hand, anything divided by 0 equals infinity. So which wins? Is it the 0? Is it the infinity? Sometimes it's one, sometimes it's the other. Sometimes neither win and it ends up being a tie, and it's something in between, right? Same thing with infinity over infinity. Infinity on the top means the value is infinite. Infinity on the bottom means that the value is 0. So which one wins? And we've seen again that sometimes one thing happens, another thing happens. With 0 times infinity, that's another indeterminate form, right? Because 0 times anything is 0, but infinity times anything is infinity. So which one wins? It's indeterminate. We don't know until we do some work. 1 raised to the infinity is interesting because anything bigger than 1 raised to the infinity goes to infinity. Anything smaller than 1 raised to the infinity goes to 0. So this is exactly in between 0 and infinity. So what does that mean? Well, it's indeterminate. Likewise with infinity raised to the 0, any number raised to the 0 equals 1, but any large value raised, any value raised to a power, any infinity raised to a power greater than 0 is infinity. So which one is it? We don't know. The 0 raised to a power is 0. Anything raised to the 0 is 1. Which one is it? Infinity minus infinity, which one is bigger? Maybe they're about the same size and it works out to be a finite answer. Sometimes this one is bigger and we get a negative infinity. Sometimes this one's bigger, we get a positive infinity. We just need to do some work to figure these out. So these are all indeterminate forms because we've got competing forces that pull our answer towards one thing or another. However, we can't just take the derivative of the 0 and the infinity just like we did with the fractions. L'Hopital's rule only works in these two indeterminate forms. So we have to do some work in order to get our original indeterminate form into this or this. All right, and a lot of times it just has to do with a little bit of algebra. For example, x goes to infinity, 1 over x goes to 0, so tangent of 0 is 0. So this is an infinity times 0. So if we can somehow turn this 0 times infinity into a fraction, then we can L'Hopital it, right? So the limit as x approaches infinity of the product, we can turn that into a quotient if we take the reciprocal of one of these two things. So we could either put a 1 over tangent of 1 over x down here, or we could put a 1 over x. 1 over x is easier, so we'll do that. Think about what we just did here. Dividing by 1 over x is the same thing as multiplying by x, but we've made it so that the denominator heads towards 0, just like the numerator, okay? So if we're going to ask the question, is this a L'Hopital situation, we're going to say the limit as x approaches infinity of the tangent of 1 over x equals the tangent of 1 over infinity, which is equal to the tangent of 0, which is 0. And then the limit as x approaches infinity of 1 over x, which is our new denominator here, is 1 over infinity, which is equal to 0. So therefore, we've got 0 over 0, which is the indeterminate form that allows for L'Hopital. So we'll apply L'Hopital's rule, take the derivative of the top, derivative of tangent is secant squared. I forget, does the argument ever change? Of course not. The argument never changes, but don't forget the chain rule. We'll take the derivative of the argument, and that's negative 1 over x squared. Hey, look at that. The derivative of the bottom is negative 1 over x squared. So those are gone, like the noble gas argon. And that gives us the limit as x approaches infinity of secant squared of 1 over x. But we already know that 1 over x approaches 0, so this is secant squared of 1 over infinity, which is secant squared, of 0, and the secant of 0 is 1, secant squared of 0 is also 1. The answer is 1. All right, So that is one type of indeterminate form. Another one that we have here is, well, if we let x go to infinity, this becomes 0. 1 plus 0 is 1. 1 raised to the infinity is indeterminate. Okay, we can't just turn this into a fraction, though, because we need a product to turn it into a fraction, not an exponential. So if we wanted to get rid of this exponential, then logarithms are a great way to go. Let's assume that this limit equals y. Let's assume that this limit exists and that value is y. So if we take the natural log of the left side of the equation and take the natural log of the right side of the equation, we're allowed to do that because it's an equation. And one of the nice things about properties of limits is that you can apply the function to the limit, or you can apply the limit to the function. It's very flexible. It's been doing its yoga. So we can flip this around and say that this is the natural log of 1 plus 1 over x raised to the, not to the 2, to the x. Where did that 2 come from? So why would we do that? Because we can expand. We can expand using properties of logarithms. We can say that the natural log of y equals, well, the limit as x approaches infinity. Well, the whole point of this was to pull this exponent out front. X times the natural log of 1 plus 1 over x. All right, so now we've got infinity, and then we've got the natural log of 1 plus 0. Oh, well, the natural log of 1 is 0. So this is infinity times 0, so that's an awful lot like this one right here. So now that we've got a product of infinity times 0, we can fractionate it like this, right? We can turn it into a fraction by taking one of the two factors, either the x or the natural log of 1 plus 1 over x, and reciprocating it. 1 over x is easier to deal with than 1 over the natural log of 1 plus 1 over x. So I'm going to leave that in the numerator, and the 1 over x is going to be our new denominator. All right? And if we take a look at the limit as x approaches infinity of the natural log of 1 plus 1 over x, well, 1 over x, 1 over infinity, I should say, is 0. So that's the natural log of 1 plus 0, or 1. And the natural log of 1 is 0. And of course, the denominator, this is the whole point, the new denominator here is also equal to 0. So we've got a 0 over 0 situation, so you know what's coming. L'Hopital. We're going to take the natural log of y equals the limit as x approaches infinity of not the original problem, but the derivative of the top and the bottom. That's our L'Hopital. So, derivative of the natural log of stuff is 1 over the stuff, because the argument never changes. But don't forget the chain rule. We'll take the derivative of stuff. And the 1 goes away, and we get the derivative of 1 over x, which is negative 1 over x squared. Lo and behold, the denominator differentiates to negative 1 over x squared. That's fancy. So that means that those are completely gone, and we get the limit as x approaches infinity of 1 over 1 plus 1 over x. Well, that's 1 over 1 plus 1 over infinity, but 1 over infinity is 0. So we get 1. And that's the mistake that people make. They'll say, oh, the answer is 1. But that's what the natural log of our answer equals. If the natural log of our answer equals 1, then our answer equals e. And this is kind of a fantastic limit. It's my favorite limit, in fact, because you wouldn't expect that something that doesn't have any natural logs in it or any e's in it to show up as having e as your final answer. But this is actually a great way to describe what e is. Okay, and this is very, very much related to the formula a equals p e to the rt, which is the formula for continuous interest. You probably learned that once upon a time, but you probably never learned where it came from. Well, this 1 over x is the portion of the interest that you're earning. This x is the amount of time. Well, it's actually the number of times it is compounded, the number of times the interest is compounded. So using the fact that the limit of this expression goes to e as we increase the frequency of our compounding, we can pretty simply derive our continuous interest formula. So that's kind of a fun, unexpected application to calculus. Hooray.